Now let's clear up a couple more consequences of the mean value theorem. So let's let f be a function whose domain is an open interval. Not going to bother to write out open the assumptions on A and B. There, A is less than B, and if you want them to be finite or infinite, that's fine. But we need f to be differentiable. And if I just say differentiable, it's like if I just say a continuous, it means differentiable at every point in its domain. So just differentiable means differentiable everywhere. Okay, then the first result is that f is increasing, so not decreasing, increasing on the interval on its domain if and only if f prime is non-negative for all x in the interval. And notice that is an if and only if statement. Part B, by contrast, is not an if and only if statement. This is if f prime is strictly positive for all x in our domain, then f is strictly increasing. That is parts A and B. Part C is f is decreasing on this interval. It's exactly what you think it should be if and only if f prime is strictly is less than or equal to 0 on that interval, meaning f prime of x is less than or equal to 0 for every x in AB. And if f prime is strictly negative on AB, then f is strictly decreasing. All right, let's go ahead and prove, say, the increasing options, parts A and B. You can get to parts C and D by multiplying by a negative 1. So let's see. So let's pick any 2 points in our domain. And then by the mean value theorem, we're going to assume that y and z are not equal, and we're going to let y be the name of the smaller one. So by the mean value theorem, there is an x that's strictly between y and z. And since y and z are in this interval, it's an interval, so x So the interval from y to z is contained in the interval from a to b, so x is also an AB such that then we can write f prime of x, that's f of y minus f of z over, actually I want this in the other order, f of z minus f of y over z minus y. So let's note some consequences, or we can also write this as f of z minus f of y is z minus y, which is positive, times f prime of x. And then, so this gives us half of part A. If f prime is always non-negative, then f prime of x is non-negative. So f of y is bigger than f of z, greater than or equal to, sorry. And then you get exactly the same three arguments that you'd expect. All right, so thus, since y and z were arbitrary, we have the one-way conditions. If f prime is non-negative, then f is increasing, and I think I will not bother writing out the other four. Or, well, I'll write out parts A and B. So part B and part D, those are both valid. Those are both proven because those were only one way. Now we need the other way of part A and part C. So conversely, for part A, suppose f is increasing. And let's let x be in our interval. F is differentiable so f prime of x, that's the limit as, let's use these letters, f of y minus f of x over y minus x exists. Now, what can we say about that difference quotient? Well, if y is bigger than x, then f of y minus f of x, that's non-negative because f is increasing and y minus x is, of course, positive. So what's our conclusion? So f of y minus f of x over y minus x, that's non-negative. And conversely, if y is less than x, then y minus x is less than 0, and f of y minus f of x less than or equal to 0, because x is bigger than y, so f of x is bigger than f of y, because, again, f is increasing. So again, we've got f of y minus f of x over y minus x greater than or equal to 0. So in either case, if y is not equal to x, then our difference quotient is non-negative. And at this point, you should be able to work through on your own the epsilon delta argument that this means that the limit indeed cannot be 0, cannot be negative. So the limit as y goes to x, f of y minus f of x all over y minus x is also non-negative, so f prime of x is non-negative, and this proves the other half of A. And you can check that C holds, or you can just multiply f by -1, and that gives you part C from part A and part D from part B if you need it. I'll point out we did not prove the converse to part B, and in fact the converse to part B is false. So here is an example. Let f of x be x cubed. F is indeed strictly increasing on any interval you want, but f prime of 0 is equal to 0, so so it is false that f prime is positive. And interesting problem to think through. What is the converse to part B that actually works? What has to be true if you want? What has to be true about the derivative for a function to be strictly increasing? I'd also like to say one thing about closed intervals. So let's let f be a function from a closed interval. This would also work for a half open, half closed interval. So f is continuous on the whole interval, and differentiable on just the interior. And then this might be an exam or a homework question. F is increasing on the entire interval, including the endpoints, if and only if F prime is positive or non-negative for all x in not the whole interval, just the inside. So you're allowed to be added the endpoints. And if F prime is strictly positive for all x in the inside, then F is strictly increasing on this on the entire interval. Last result in section 2.3 is proposition 2.3.10. So here's how this works. We're going to let I be an interval. And let's let F be a function whose domain is our interval I. And we're going to say that F has to be continuous and differentiable. And remember, we have defined what it means to be differentiable at an endpoint. It just means your limit only sees points in the interval. And we are also going to require that F be injective. So F has to be 1 to 1 on this interval. And so 1-to-1 functions, if you restrict to their image so that they're surjective, they've got an inverse. We spent a lot of time talking about inverses back in section 1.7. I thought an inverse of a continuous function is continuous. I thought that belonged in the section on continuous functions, but your book thinks it belongs here next to proposition 2.3.10, and here is why. Let's let x be a point in our interval, and we'll assume that f prime of x, it has to exist because we're assuming f prime exists everywhere, so let's assume f prime is not equal to 0. And the conclusion is that then f inverse is differentiable at the point f of x, and let's give f of x a name, let's call it zeta, and f inverse, the derivative of f inverse prime of zeta, I can even tell you what that is. That is 1 divided by f prime of x. Now, before we prove this, let's write down a couple of things that we know. So from Math 2803, from Transitions to Advanced Mathematics, f inverse, that's a function whose domain is the image, f of I back to I. That is a function. it is well defined, and is also bijective. F is injective by assumption. It's bijective onto the image by definition of image. So you learned in 2803, any bijection has an inverse, and the inverse is well defined. That just means it really exists. It's not something that looks like a function, but isn't. It's really a function. So then let's write down a couple of other things we know. So we've got corollary 1.7.8. Says that f of I is an interval. And I'm going to point out every point in an interval is a limit point. And remember, we said limits and derivatives are only defined at limit points, so we don't have to worry about that. So zeta is a limit point. Of f of I. That's because zeta equals f of x. So it's certainly in f of I. And then it's a limit point because every point in an interval is a limit point. What else do we know? We know from proposition 2.3.8, we know that f is any continuous one-to-one function on an interval has to be strictly monotonic, either strictly increasing or strictly decreasing. And the last thing I want to remind you that we already know from a few videos back is that f inverse is continuous on its domain, which is f of I. Now we are going to do the same trick we used in the proof of the chain rule. We're going to let capital F of x, this is a piecewise defined function, capital F of y, it's going to be 0 if y is equal to x, and it's going to be f of y minus f of x over y minus x. Then we're going to subtract off f prime of x. And that's if y is not equal to x. And we've done this before. Or as long as y is in the domain of little f. Then f is a function whose domain is all of I, including the real numbers. And big F is continuous at x by the definition of derivative. The limit as y goes to x of big F of y is 0 because your difference quotient is heading towards f prime. So by corollary 2.1.3, and we can write f of y minus f of x is equal to y minus x times f prime of x plus big F of y. And this is true for all y in our domain I. So we've seen this before, and this is going to be very important in chapter 6, which is why I'm emphasizing it so much now. Now what we're going to do is we're going to rewrite that inequality in terms of f inverses. So let's let omega be a point in f of I minus zeta, and we recall from the proposition statement that zeta is f of x. And then f inverse of omega is in I, so we can rewrite our above equation as f of, let's say, f inverse of omega minus f of x, which is zeta. That's equal to y is f inverse of omega, and then x is f inverse of zeta. And then we put f prime of x, we'll leave that as f prime of x, and then capital F, and then y, remember, is f inverse of omega. So this is just the same formula we've got up here, except that I have gone ahead and replaced y by f inverse of omega and x by f inverse of zeta, or f of x by zeta. And then notice that f of f inverse of omega is in fact omega, so our left-hand side simplifies a little bit down to omega minus zeta. Now, also our left-hand side, if omega is not equal to zeta, then the far left-hand side is not zero. And that means that the far right-hand side can't be zero. This f inverse of omega minus f inverse of zeta can't be zero, and also f prime plus big F of f inverse of omega is not zero. So notice if omega is in f of I minus zeta, then f prime of x plus big F of f inverse of omega is not equal to zero. And in fact, this is true even without the condition. This is true for any omega in f of I, because if omega is equal to zeta, then an f inverse of zeta is x, and then big F of x is zero, and little f prime of x is not zero. So this is not zero even if omega is equal to zeta. However, we are going to need to assume that omega is not equal to zeta for this next step. Then let's write f inverse of omega minus f inverse of zeta over omega minus zeta. That's equal to 1 over f prime of x plus big F of f inverse of zeta. All right, our right-hand side always exists. We're never dividing by zero. Our left-hand side, we are dividing by zero a little bit. And then f inverse is continuous at zeta, and big F is continuous at x, which we remember is f inverse of zeta. So big F composed with little f inverse is going to be continuous at zeta, and that's by proposition 1.7.4. So we've got that the limit as omega goes to zeta, f prime of x, which is just a constant, plus big F of f inverse of, I just realized I've been writing a bunch of big F of F inverse of zetas when they should be big F of F inverse of omegas, so I will go back and fix that. Right, getting back to the main point, this limit, big F is going to be just F prime of X because that's a constant as far as omega knows. Then that's big F of F inverse of zeta, and that's F prime of X plus big F of X is just F prime of X. And this is all by corollary 2.1.3, and because big F is continuous at X and is also 0 at X. And then we've got that F prime of X is not equal to 0, and F prime of X plus big F of F inverse of omega, that's also not equal to 0 for any omega in F of I. So by proposition 2.1.5, the limit as omega goes to zeta 1 over F prime of X plus big F of F inverse of omega. That limit is just 1 over F prime of X. But 1 over F prime of X plus big F of F inverse of omega, that's, we had that above, that's F inverse of omega minus F inverse of zeta all over omega minus zeta if omega is in F of I, well, minus zeta. So we've got that the limit as omega approaches zeta, is just the limit we saw, is just the limit of the same thing, the limit we saw before, and it exists. So F inverse prime of zeta is 1 over F prime of X and exists. And that is what we were trying to prove here. So that completes the proof. So as an example, let n be a natural number and f of x be x to the n. F is 1-to-1, continuous and differentiable. On certainly it's injective on the non-negative numbers. If n is odd, it's injective on all the real numbers. If n is even, you have to take just you have to throw away the negatives to make it 1-to-1. And f prime of x is not equal to 0 on the interval from 0 to infinity. And also, you can prove using the intermediate value theorem, f of 0 infinity is 0 infinity. So we've got that f inverse that is differentiable. And furthermore, f inverse prime of x, that's 1 over f prime of f inverse of x. That's 1 over n times f inverse of x to the n minus 1. And then recall that we define x to the 1 over n to be f inverse of x. So f inverse prime of x now is 1 over n and then x to the n minus 1 over n. Which, if you prefer, you can write as 1 over n x to the 1 over n minus 1. So the power rule holds for these fractional powers. The power rule that you know and love from freshman calculus still holds. And also notice that f inverse prime of 0 generally doesn't exist. If you remember how, say, the square root of the cube would work, generally you're going to have infinite slope at 0, so your derivative is not going to exist. We're going to skip most of section 2.4 because I want to make sure we have time for all of sections 2.5, 3.1, 3.2, 3.3, 3.4, because they're all important, and I think they're also all more interesting than most of section 2.4, but I did want to do one example. So let's define the following function. It's a piecewise defined function. So f of x, or f2 of x, this function is going to be x squared times the sine of 1 over x if x is not equal to 0, because, of course, sine 1 over 0 is no good, and it's going to be 0 if x is equal to 0. Right. Then, if x is not equal to 0, then we can use the usual rules of differentiation. We can get f2 prime of x is 2x sine 1 over x. And then by the product rule and the chain rule, this is minus cosine 1 over x. And notice in particular that the limit as x goes to 0, 2x sine 1 over x. But the squeeze theorem, if you're familiar with it, just because sine 1 over x is always between minus 1 and 1, this limit exists and is 0, and cosine 1 over x doesn't have a limit as x goes to 0, so limit as x goes to 0, f2 prime of x, that does not exist. And then but I'll point out to you x squared sine if x is not equal to 0, then f2 of x minus f2 of 0 over x minus 0. Simplify it a bunch, cancel out the things that are 0, you get x sine 1 over x. So if you take the limit as x goes to 0, that limit is indeed 0, and in particular exists. So f2 prime of 0 exists and equals 0. And the point of this example is that, so there are some functions that are continuous and differentiable. This function in particular is differentiable everywhere, but the derivative is not continuous. So that's what this example is getting at. It's a nice differentiable function, but its derivative isn't continuous. It's 0. Even though the derivative exists everywhere, it's not continuous.